And so what do I want to ask? Let's ask some basic questions. Where is f prime of x equal to 0? And then B, what about f prime of x, say less than 0, f prime of x greater than 0? I think we can, let's make this a little bit smaller. Okay. So the first question is, where do we have a derivative of 0? Now, a lot of you might be kind of used to recognizing it from the graph right away. That's fine. And then we'll catch everyone else up to speed. So where do we think the derivative is equal to 0? Now, as you're thinking about this question, how might you answer that question? Okay, so first of all, we don't know much about the derivative quite just yet. All we have is a very basic understanding, right? We have this idea that the derivative at a point is the slope of the tangent line at that point. So what you should be thinking about is thinking about secant lines, right, and tangent lines, right? If you want to figure out, okay, what is the tangent line say at this point right here? Let's actually look at x equals 3, right? You might look at nearby secant lines and then try to figure out what kind of lines do those secant lines all converge upon, right? And they all seem to converge upon that. So that's how you might want to think about tangent lines. Now, a few people in chat said, so let's see, Thomas says the derivative is 0 at the peak. Swarnima says at the max and mins. Miriam says at x equals 2, 4, and 8. Simran says where the slope changes from positive to negative or negative to positive. Okay, so let's see. So I'm going to highlight those points. So we said x equals 2, x equals 4, and x equals 8. Can you scroll up a little, please, so I can see the question? The question right now is, where is f prime of x equal to 0? Okay, so let's see. So is the slope of the tangent line equal to 0 at x equals 2? All right, so let's see. So let's mark a point at x equals 2, and let's look at the tangent line. Well, right now, the only way I can really visualize this is by looking at secant lines. So I'm going to draw a few points that are close by on either side and look at what's happening to these secant lines. Okay, so for the green secant lines, I have something that looks like this. And then for the pink secant lines, I have something that looks like this. All right. And so as the pink or green lines come in towards the orange point, right, what is actually happening? So the pink lines and the green lines, they seem to be converging upon, as they come closer to orange, right, as h approaches 0, right, as the unfixed point approaches the fixed point. Do the green and pink lines seem to converge upon the same line? And yes, they seem to be converging upon this line right in the middle. And we will learn later analytically, we can actually prove that if a function has a local min or local max, like in this case, so if we have a function that has a peak or a valley, at that peak or at that valley, where I have a local minimum or local maximum, if the function has a derivative, it must be 0. So we will learn that in a bit more detail later on. So we definitely have x equals 2, 4, and 8, right? They all have this property that they have these. Sorry, I forget, I can always do a dashed line now. They have these horizontal tangent lines. Nashika, do you think there are any other points? Oh, never mind. Miriam saved you. Miriam has an answer. Miriam says you think 6 also. But Miriam, that kind of goes against what everyone else was saying. Are you ready to go against the whole chat? Miriam's like, yeah, because I'm right. So Miriam actually does point out something very peculiar. So what about x equals 6? So maybe I haven't drawn it exactly accurately, but I did mean for a horizontal tangent line to also occur at 6. So a horizontal tangent line does not necessarily occur where you have a local min or local max, or where there's this transition from increasing to decreasing. I mean, it's almost intuitive that that happens that way, but sometimes we get a function like this at x equals 6, where it decreases, it comes to kind of a flat part, and then it keeps on decreasing. This is kind of like this is like y equals negative x cubed. So think about sitting on like a saddle, right? So it's kind of like that. That's usually called a saddle point, in fact. In more than one dimension, we get actually things that really do look like horses' saddles. That's what they're called, saddle points. So in fact, there's also a tangent line at x equals 6. And again, how can you see that? Just look at the secant lines, right? What is happening with the secant lines? Again, I do apologize if it's not clear from how I drew it, but the idea is, okay, let's look at these two secant lines, right? And what's happening? So I have one secant line that looks like this, then I'll have another secant line that looks like that, then like that, and like that, and then they all seem to be converging upon this horizontal line. But that's the idea. So x equals 6 also has a horizontal tangent line. So be on the lookout for those saddle points. So 2, 4, 6, and 8. Okay, so now let's look at part B. Okay, so now I want to know, where is f prime? I think I said negative. So where is f prime less than 0? So let's highlight those special points, 2, 4, 6, 8. That was where the derivative was 0. And now I want to highlight, where is f prime less than 0? Let's highlight that in red. So what do you think here? F prime of x is less than 0 on. So when the function is decreasing, right? So that's a good graphical interpretation, right? Because if I have a negative tangent line, right? If I have some function here, so here's a negative tangent line, and if that's supposed to be tangent to the graph at, say, some point, that means the function must kind of look like that near that point. So the function is decreasing, right? As the x values increase, the y values decrease. Okay, so where would you say this function is decreasing? Now, I do want to say decreasing does not necessarily mean derivative is less than 0. Okay, but most of the time it does. I mean, there's some exceptions, and we'll see they're not exactly the same thing. So first, let's answer the question, where is f prime of x less than 0? Where do I have a negative slope tangent line, right? Where does the tangent line have a negative slope? What do we think? Camelia, what do you think? Can you give us at least some x values where you think the tangent line has a negative slope? Right, we've discussed so far x values where the tangent line has 0 slope. Can you give us some x values where the tangent line has negative slope? Okay, so Naomi says x equals 1 and 5 and 7. Well, let's not do individual x values, because we're definitely going to want a whole interval. Can we now give an interval? Maya is 0 minus 2. Is that how we write intervals, Maya? Maya Nicole? So let's get that interval notation. Okay, good. So 0, 2, right? Because I want to see if you're including the endpoints or not. We shouldn't be. So all of the tangent lines in this highlighted interval have negative slope. Okay, all right? So here's one tangent line. Let's do that actually in blue so you can see it. So here's one tangent line, here's another tangent line, here's another tangent line, and so on. Right, they all have negative slope. So wherever the function is actually decreasing. Okay, so let's see. So 0 to 2, 4 to 6, and then 6 to 8. Now, Camelia, you included x equals 0, but we should not include x equals 0. What do you guys think the derivative is at x equals 0? What do we think about f prime of 0? Is it negative? Is it positive? Is it 0? What do we think about that? Is Camelia right? Justin, you said we don't know. Why do you say we don't know, Justin? Camelia says it's 0. Nishika says undefined. Sarah says could be 0. Isn't it an endpoint? X equals 0 is an endpoint of the domain here, yes. It could be positive, or negative, or 0. So the derivative at f prime of 0, so f prime of 0 is actually undefined. The derivative at 0 is undefined. Why is f prime of 0 actually undefined? So I'm going to write down, so first of all, the derivative is negative on 0 to union 4 to 6, union 6 to 8. And then we're going to say kind of a note here. So note f prime of 0 does not exist. So Joshua says we can't take the limit because there is no limit from the left. That's right. So for derivatives, I'm always doing the limit as h approaches 0, and I need secant lines on both sides. So by default, if I have a boundary point of my domain, so in this case, x equals 0 is a boundary point of my domain, automatically the derivative cannot exist at a boundary point, always. Okay. All right. I want to make another note here. What if I actually asked the question, where is f decreasing? And I want to, I'm asking this because I want to emphasize that asking where the derivative is negative is not the same thing as asking where is the function decreasing. What does it mean to say that a function is decreasing? So for instance, if I were to claim that this function is decreasing on the set 3 to 5, it means that I can pick any two x values in the interval 3 to 5, and the larger x value always has a smaller y value. That's what decreasing means. So is this function decreasing on 3 to 5? No, because for instance, I can choose, say, x equals 3 and x equals 4, and the larger x value actually has a bigger y value. So it contradicts that definition of decreasing. Okay? So where would you say this function is decreasing? So 1.5 to 2? Why only 1.5? What about all this part? What about from 0 to 1.5? So the function is actually decreasing. First of all, we don't use the union symbol for decreasing, again, because we can't necessarily pick numbers from each interval. So the function f is decreasing on the intervals 0 to and 4 to 8, and that's it. Notice I'm using closed brackets here. Why? Does this agree with the definition of decreasing? Can I choose any two x values in the interval 0 to 2, and the larger x value always has the smaller y value? Yes. I mean, even if I choose x equals 0 and x equals 2, or even if I choose x equals 1 and x equals 2, right? No, the function is defined at x equals 0. It's the derivative that's not defined at x equals 0. But f of 0 is defined. There's a closed hole there. So I just want to point that out to you. And notice that x equals 6, the function is actually decreasing on this whole interval. Even though the tangent line is horizontal at x equals 6, the function is decreasing on the whole interval. Again, is it true that if I pick any two x values in the interval 4 to 8, the larger x value always has the smaller y value? And yes, that is true. right? I don't need to exclude 6 or make, like split this up into 2 intervals. So you can see that f prime less than 0 is very closely linked to f being decreasing, but they're not quite the same. Okay. And then let's just finish this up. So now I want, where is the function have a positive derivative? So again, let's just highlight where the function had a 0 derivative. And now let's highlight where the function has a positive derivative. And I will also note, where is f increasing? Okay, so where is the derivative positive in this case? And again, if you're not sure, think about tangent lines, right? Try drawing some tangent lines, and if the slope of the tangent line is positive, that means the function is the function has a positive derivative there. So yeah, x equals 3 definitely has one, but obviously there's more than just x equals 3. So let's see. So a few people are saying from 2 to 4, good. And then Simran said 8 to question mark, 8 to infinity, 8 to 9. So the idea was this was supposed to suggest 8 to infinity. So I'm just going to write that, although the graph can't really show that. But I'm going to say 2 to 4 union 8 to infinity. And where is the function increasing? The function is increasing on the interval 2 to 4 and from 8 to infinity, including the endpoints. Okay. Now I have one kind of quick question. So here's our original graph. Is that a bracket before 2? Yes. For the increasing. So here's a bonus question. What if I shift the graph up or down? So for instance, what if I move my x-axis, let's say up here? So now all the y values have essentially been shifted down by, say, 2 units or whatever. What happens to all our answers? Where does the function have f prime equals 0? Less than 0, greater than 0. So let's see, Miriam says nothing changes, right? Nothing changes. So shifting a graph up and down does not affect the slope. What happens if I did it the other way? What if I shifted it to the left or the right? What if I did it this way? So now the graph has been shifted to the left, say like 2.5 units. What happens to all our answers? Still the same? So Camelia, I ask you, where is the derivative negative in this case? So keep in mind, all these tick marks are now different. They're all to the left 2.5. So for instance, this would be, say, negative 2.5, negative 1.5, 1.5, 4.5, and so on. So Nishika says still the same, but different. So I think I know what you mean, but can someone either say what Nishika means or Nishika can clarify? They're the same, but different. It's increasing and decreasing at the same places, but the values are different. So when you say same places, so this function is still increasing from 2 to 4? The intervals are different, right? So how have all these intervals actually changed? How have all our answers changed? They would shift with the graph. So can we be more precise? I said that this shifted to the left 2.5 units. So all the x values decreased. Right, so all the x values in every interval have shifted to the left 2.5 units as well. Right. So shifting a graph up and down does not change the slopes, obviously, it does not change the derivative, but shifting it to the left and right does, right? Because that changes the x values, right? The slopes themselves kind of still have not really changed, but they have because they occur at different x values. So kind of keep that in mind when we're doing derivatives.